Okay, so today we're going to continue talking about atomic structure and atomic theory. So we're going to move on to 4.2 now in physical science. So we already talked about some parts of atomic theory. We talked about Dalton and we talked about his theories. We talked about the properties of subatomic particles. We talked about Thomson. We talked about and we talked about Rutherford. Okay. Now we're going to talk about Chadwick and the neutrons, and then we're going to talk about comparing subatomic particles as well as mass number and atomic number. So James Chadwick comes along after Rutherford and Thomson, and he discovers the neutron, which is a neutral subatomic particle that's found in the nucleus of an atom. This one was probably the hardest one to discover after the other two, because this one didn't have a charge, but they knew it was there because it did have uh, mass. So neutron, neutral. To compare the subatomic particles, they can be distinguished by their mass, their charge, as well as their location in the atom. There's a chart in 4.2 that goes through this with you. As far as protons and neutrons go, these have almost equal mass. And when we talk about the atomic mass of an atom, we're only using the mass of the protons plus the mass of the neutrons. We don't count electrons because electrons have charge that's equal in size to that of protons, but electrons are way, way, way smaller. It takes about, says 2,000 electrons to equal the mass of one proton. So we don't count the mass of electrons, okay? Neutrons have no charge as we discussed, so protons, positive charge, electrons account for the negative charge, and the mass is from the protons and the neutrons. It's important to note that the protons and the neutrons are located inside the nucleus of the atom or the center, like we see in the background here, and the electrons would be orbiting around the outsides in a space that we call the electron cloud. If we talk more about this, if we want to compare the subatomic particles some more, everything that we know about them is based off of what we know about the nucleus and how particles behave. We don't necessarily have an instrument that shows us the inside of the atom. So an important part of this section is to talk about atomic number and mass number. So Dalton predicted that atoms of any element are different from atoms of all other elements. And these atoms that we're looking at all have a unique atomic number, okay? The atomic number, when we're talking about this, refers to the number of protons that the element has. So helium is atomic number 2. That also means that helium has 2 protons. Hydrogen is atomic number 1. Hydrogen has 1 proton. If we go back to this previous slide, Na, which is sodium, is atomic number 11. So sodium has 11 protons. Okay? Every element has a unique atomic number. No two elements have the same atomic number. So all elements have a different number of protons that are in them. Okay? If we're not talking about isotopes, which we'll talk about a bit later, not only do all these elements have different numbers of protons that are based on their atomic number, but whatever their atomic number is equal to their number of protons and also equal to their number of electrons, which we'll talk about in a bit. So it goes without saying that if you're somehow able to change the number of protons, you change the element. So instead of having 2 protons, if it had 3 protons, it would become lithium. If it had 47 protons, it would become silver. Okay? Atoms of different elements have different number of protons, as I mentioned, and you could use atomic numbers to refer to elements like names and symbols because each element has a unique atomic number. It says on here that each positive charge is balanced by a negative charge because atoms are neutral. So as I mentioned, if you have 2 protons, you have 2 electrons. If you have 3 protons, you have 3 electrons. The only exception would be is if it's an ion. We talk about mass numbers. I mentioned before the mass number is determined by not only the protons, but that's protons plus the number of neutrons in the nucleus of an atom. This can actually vary. So even though each element has the same number of protons, no matter what sample of the element you have, sometimes it has a different number of neutrons, and this is called an isotope. So if we want to know the number of neutrons an atom has, you simply just have to use this formula. Mass number, okay, minus atomic number, will tell you the number of neutrons. So if I have carbon 14, which is a mass number of 14, and I have 6 protons, 14 minus 6 would tell me that I have 8 neutrons. As I mentioned, isotopes are the same element but a different number of neutrons. So every atom of a given element does have the same number of protons and electrons, but not neutrons. Okay, so for instance here, hydrogen. Here's hydrogen with no neutrons. Here's hydrogen with 1 neutron. Here's hydrogen with 2 neutrons. These are all hydrogen. They all have 1 proton, but some have no neutrons, some have 1, and some have 2 even. Isotopes, again, by definition, are atoms of the same element, but they have a different number of neutrons, and therefore they have different mass numbers. So for instance, if you look down here, lithium, lithium, lithium. These are all lithium. They all have 3 protons, but this one has a mass number of 6, this one has 7, this one has 8. So if you do the math, find out the number of neutrons, 6 minus 3, this would have 3 neutrons, 7 minus 3, this would have 4 neutrons, 8 minus 3, this would have 5 neutrons. Isotopes of an element have the same atomic number, but different masses because they have a different number of neutrons. As I just mentioned on the previous slide, here's another example. Oxygen 16, 17, 18. Oxygen has 8 protons, so 16 minus 8, there would be 8 neutrons in the first one. 17 minus 8, there would be 9 neutrons in the second one. 18 minus 8, there will be 10 neutrons in the third sample. This is just showing you carbon, okay? Carbon 12, carbon 13, carbon 14. This is the percent of each you find in the world. So carbon 12 is by and far the most common carbon, with 98.9% of carbon being carbon 12. When they actually determine the atomic mass on the periodic table of elements, it's the average of these depending on how much of each there is. That's why carbon has close to 12 as their atomic mass on the table. Okay, and that is it for 4.2. So we'll be practicing this more throughout the week now.